Okay, here we are. We made it to the end. This is the final vignette in the final chapter. Well, we're almost to the end. Let's jump in and talk about model selection. So we're going to go right to R this time. I'm going to look at this data set that's called the boss data, and it has as the responses how employees rate their boss based on a number of attributes, like does the boss allow special privileges, do they give raises based on performance, and so on. So we'll read in this data, and we're going to straight away fit a multiple linear regression using all of the inputs. So I'm going to call this the full fit, and you'll see why in just a moment. Now here's a thing you maybe didn't know you could do. If you put a dot and give it the data frame with all of the data, then it will take the y as the output and everything else as inputs. So that's a nice little shorthand. And when you look at the summary of the fit, you can see that there's 6 inputs and there's an intercept, and that the first input seems to be useful for predicting the output because its p-value for the null hypothesis that the coefficient is 0 is less than 5%. But none of the other inputs have p-values indicating that those inputs are useful. And the reason that this happens, in this example anyway, this is happening because the inputs are highly multicollinear, which basically means that they're correlated. There's a bit more on multicollinearity in the book that I don't want to get into here, but if I just show you the correlation between the sum of the columns of x, you can see that x2 is like 50% correlated with x3 and 64% correlated with x4, and x3 is 45% correlated with x4. So there's a lot of correlation in the x's, which means they're not providing independent information about the boss, especially as relates to one another. So it could be difficult for them to independently contribute to predicting the output y if they're all in the linear model together. So I want to look at a simpler fit. Involves just the first 2 inputs. So I'm going to fit, I'm going to call it the base model, and again you'll see why in a little minute here. And I'm just going to do x1 and x2. Okay, so I've got this fit. And again, x1 is useful, but now we can see that even though we took away x3 through x6, x2 is still possibly not useful for predicting y. And I don't want to dwell on that too much. What I want to focus on is which of these 2 models is better. Okay, so one of them is sort of simpler and easier to explain. It's more parsimonious, less likely to overfit, and that's the one with just 2 coefficients. The one with 6 coefficients is richer, but more complicated, more difficult to explain, less parsimonious. So maybe we like the simpler model kind of just based on aesthetic grounds, but how do we make an argument that's statistical? Okay, so one way to measure is by looking at R squared. So R squared is the correlation between the inputs and the outputs squared, but we have many inputs, so actually we're going to look at the correlation between the output and what we predict using all of the inputs. So that's how you extend R squared to multiple inputs x. Okay, so I'm going to call it R squared F is going to be the correlation between the output and the full fitted. Okay, so that's full, maybe that is called fitted values, let's see, fitted values squared, and I have to do boss. Okay, so that's R2F. And another way that you can get R2F is you can do summary full R squared, and that is the same number. So that's the way I'm going to use going forward, but I just wanted to show you that the R squared is the correlation between the data values and the fitted values. And then I'm going to do the same thing for the base model, the smaller one, and then I'm going to look at their difference. Their R2 diff is R2F minus R2B. So R2 diff. Okay, so there's a 2.5% difference. R2F is bigger than R2B, and that's always going to happen. If you have one model that has more coefficients, the full one, than the one that has less, the full one is going to have a smaller residual sum of squares. We know that R squared involves looking at sums of squares because of ANOVA. We talked a lot about that in chapter 6. So we're always going to have that the bigger model has a bigger R squared than the smaller model, so it has a better fit, but you know, is it really better? It's always going to have a bigger value. In this case, the amount better it is like 2.5%, and what we really want to know is this extra 2.5% worth the 4 extra slopes or extra estimated parameters? So the number of parameters involved in the full fit is 7, and the number of parameters involved in the base fit is 3. So there are 4 extra parameters. So P diff is PF minus PB. So the real question is 4 parameters worth, is 2.5% worth the cost of 4 extra additional parameters, extra complexity? Okay, so let's go back over to, well, not back over, let's go to the whiteboard and be more specific about what we're trying to solve here. So how to select from 2 nested MLR models. So they're nested because one of them is a special case of the other. Our base model has the same coefficients as in the full model, but it's missing some of them. And one good statistic for that comparison is R squared from the 2 fits, which is the correlation between the outputs and their fitted values. So we're going to write down some hypotheses. I'm going to take inspiration from ANOVA, which has an R squared connection. And I'm going to take the null hypothesis to be that all of the extra coefficients from the full model beyond the base one, so I'll call this P full. Man, struggling. All these extra coefficients in the full model that are not in the base model are 0, versus the alternative that at least one of these coefficients is not 0 for j bigger than p base. Okay? So that's easy to write down. Maybe hard to think about how you would do the test, except if you try and do it by simulation. So I'm going to say it's easy to virtualize an R squared comparison with these hypotheses. And then we're going to come back to talk about how the math works in just a minute. So let's go back over to R. I'm going to do a little bit of setup to simulate from the null hypothesis, which is basically that the base model is best. And the alternative hypothesis is that the full model is better. Okay, put that in parentheses to be consistent. Okay, so I need to have all of the predictors in my code here. So I'm going to pull this out of the boss data frame, and I have n data points in my regression, and I'm going to put together a data frame that has, I just want to call it, I kind of need 2 copies of my boss data frame in my code. So, and here a little more setup. So the regression coefficients in the null hypothesis are going to be the ones from the base fit, and then I'm going to repeat 0 for pdiff remaining coefficients. Okay, so under the null hypothesis, these are my coefficients, but expanded out to fill out the full 6 plus 1 coefficients in the full model. Okay, and when I use those regression coefficients, the thing that I predict is the intercept plus x times the slopes. Okay, so I'm just getting another shorthand that I think is going to be useful in my script. And then the predicted uncertainty, also from the base fit, is sigma squared that I can get from my base fit. So these are all just things I extract from the base fit. Okay, now for the simulation. And you'll see how all these things are used. So I'm going to do my usual 100,000. And I'm going to save R2s. So I'm going to do it from the full model and from the base model. For my n1 to n. Okay, so here we go. I am just going to take the simulated, so simulate from sigma squared. So the real way to do this is with an inverse chi-squared distribution, but I actually took a little cheat in my own script, but I did give a comment, could draw from inverse chi-squared. And you can check the book for that, but I'm just trying to cut down on the amount of work that I'm doing here. So ys, I'm going to do R norm, n values that have a mean of mu under the base model with this variance. So I'm generating virtual data that have the same coefficients as the base model, right, with that mean and a variance that comes from the base model. So I'm really just simulate from the null hypothesis. That's what I'm doing here. Okay, so now I've got data under the null hypothesis. Use data under the null hypothesis to do a full fit. Okay, so I'm going to build a data frame that has as its y values the simulated ones, so that I can do fits. So I'm going to do now do fits. So my full fit is LM, Y, twiddle, X1 plus, I could use the shorthand here, but in my notes I wrote it all out. So I'm going to stick with that. So look how I'm using the data that I just created that has simulated Y values under the null hypothesis, where the coefficients involved in mu only have the first two that are non-zero. Okay, so that's the full fit, and then the base fit is just this. So I generated data under the null hypothesis, and now I'm going to see how these two fits fit for those data, and I'm going to extract my statistic. Okay, so I'm going to do R2FS I summary FS R squared R2BS summary BS squared. And then I also need to save their difference, R2 diffs. Okay, so notice how I followed the setup that we always have. It's a little bit complicated, but I'm generating data under the null hypothesis, then I'm doing fits under the null and alternative hypothesis, and looking at their difference in R squareds. So this is a little slow to run. Hopefully I haven't, I made, I've just got the parentheses in the wrong place. Hopefully there are no more and it'll just go. Okay, what do we think R2 FSI is? Oh, why is that quotes? Summary, R2FS, rep, NA. Let's just rerun this and then, okay, it was fine. It was just from an earlier mistake. Okay, so while it's running, we have the usual visuals for this, right? I'm going to look at a histogram of R2 diffs, and then I'm going to put my observed R2 diff on that visual and make it red. So I think this takes a minute or so, so I have some time to fill. So what my statistic is really the difference in R squared values. So that's really what I'm using, although in my code I am saving both sets of R squared values. And the reason that I'm saving both of them is because I want to show you a slightly different statistic in a moment, something that's more common when you're not doing the simulation. Okay, maybe I need to kill a little bit more time while this is running. So why don't I get a head start on the math version. So the math version of all this is also similar to ANOVA. You look at ratios of mean squared errors, which can be expressed as R squared values. So there's a duality in mean squareds and R squareds. So what we look at is the sum of squared errors from the full model minus the sum of squared errors from the base model, and take that number and divide by the difference in the number of parameters. So that's what I mean about mean squareds, right? Because we're dividing by how many parameters there are. Divided by SSE full divided by n minus p full. So that's the statistic that gets called F, and P delta is our P base minus P full. And you can also calculate that by looking at a difference in R squareds divided by P delta over 1 minus R squared full divided by n minus P delta. So you'll get the same quantity if you do the calculation this way, where R squared delta is R squared full minus R squared base. Wow, it's still going. I did 1 million. So it's going to take 10 times longer than I thought it would. Why don't I stop that and see where we were? We were less than a quarter of the way, or just about a quarter of the way there. So let's rerun it with a smaller one. That'll come back quicker. Apologies for that. That's what happens for doing it live. And you can show that the distribution of this F statistic follows an F distribution, surprise, surprise, with parameters P delta and n minus P full. So that's the math version. Of course, I didn't derive it for you. I just quoted it for you. And the punchline is that, you don't have to be a brilliant mathematician to work out this F statistic and its distribution, because you can just do the simulation and wait a little bit. So when you make a mistake, I guess, and do too many simulations, you might have to wait a little bit longer. But this guy should probably be done in, I don't know, probably less than another minute, and then we'll see what the visual looks like. Okay, so just in anticipation of that, I'm going to reveal the plots. That was a plot that we made last time. And then we're going to look at this histogram of our two diffs. So it should pop right up when the simulation is done. And we'll be able to, and the visual is going to be, there's the visual. Okay, so it's done, and I don't think we're going to reject the null hypothesis. Doesn't look like a reject, but we can do a p-value. Okay, so F statistic p-values are always positive, so always right-tailed. So mean of R2 diff bigger than R2 diffs. Okay, so 68% fail to reject the null hypothesis and conclude that the base model is good enough. Okay, so let's calculate this F statistic now the math way. Since we set that up, let's put the math back up just to make sure we're doing it correctly. So F is, I'm going to do it with the R squared since that's what I have handy. So R2F minus R2B, or I could have used R2 diff divided by P diff, and then that whole thing divided by 1 minus R2F. I'm going to probably need a second set of parentheses here, divided by n minus PF. Okay, so there's the F statistic, and then p-value is right-tailed. So PF, F, P diff, and n minus PF, lower tail equals false. Okay, so same conclusion, not same accept of the null hypothesis, but similar, not identical, p-value. And that happens because in this case we're using a different statistic. We're not just looking at the difference in r squareds, but we've got some nonlinear function of some other quantity involved. So it's not just a rescaling of the difference in r squareds. So we don't get exactly the same p-value, but if we use f in our simulation instead, what I mean by that is to generate synthetic or virtual f's from the R2 diffs in the same way. Okay, so I guess I probably don't need all these parentheses, but I'll copy them anyway. Okay, so we do the same statistic with the samples and then do the same p-value calculation. I will get a closer, it's not really that much closer, is it? It's a lot closer in my own notes, unless I've got something wrong here. I don't see anything wrong. Maybe I'm just unlucky with my sort of smaller simulation. Yeah, I was hoping that would be more similar to 0.68, like it is in the book. Maybe I made a mistake. That would be fitting for the very last vignette, but I don't see it. Oh well.